The aerial to be described is 25 meters, that is, about 82 feet in diameter. Preparation of the specifications and finding a site for the aerial were matters for collaboration between the Radio and Space Research Station of the Science Research Council and the Ministry of Public Building and Works. Chilbolton is a suitable site from the scientific point of view and is not too far from the parent station at Slough. Furthermore, it is on chalk, which is a good foundation material for the concrete tower which supports the aerial. The horizon is low enough in most directions for low-angle radio paths to be investigated, yet it is high enough for some screening from unwanted radio transmissions to be obtained. Ready mixed concrete with mild steel reinforcement was used for the construction of the tower, over 2,000 tons of it. Once the pouring started, it had to be continued without pause right up to the level of the particular section of formwork in use. In one of these operations, 750 tons of concrete were poured in 12 hours. A support cage was embedded in the top of the tower. On this is bolted a capping ring which supports the azimuth bearing, fitted on top of the tower, ready for the rest of the rotating equipment. First, the main equipment cabin, clad with aluminium, had to be lifted up and placed around the tower, and rotates in azimuth with the aerial. In the upper floor go the motor generator sets and switchgear for the aerial drives. The lower station for some of the radio apparatus which will be used. The bronze gear ring, seen being lifted onto the top of the tower, is a very accurately cut gear wheel which rotates with the aerial in azimuth. It drives the digital encoders which measure the angle through which the aerial has turned, to the nearest 1/8 of a minute of arc. This steel cone, seen here, is part of the cable. Aerial is the rotating platform which contains the motor gearboxes and data pickoffs for both the azimuth and elevation drives. This weighs 80 tons, and it rotates on a 13-foot diameter wire race ball bearing already in position on the tower. This bearing must support 400 tons of rotating equipment and withstand gale forces with a large factor of safety to ensure long life. The aerial is driven in elevation by two semicircular racks, one on each side of the rotating platform. The pinions which engage with the racks are connected together by a torque tube to give increased rigidity and to prevent differential movement. One of the toothed racks on its massive mounting is being offered up to minimize friction. During the course of manufacture of the racks with the bearing housing. The cranes used on site are of interest. There were few of this lifting capacity available in the country. Is one of the support structures. There are two of these, one to be placed above each rack. Again, rigid fabrications are used and each weighs 20 tons. At the top, these sliding joints permit radial movement of the strong ring brought about by differential thermal expansion. Part of the backing structure just mentioned is assembled on the ground ready for lifting. The object is to set the feet of the sliding joints and then to insert the fitted bolts. All the bolts went in without undue assistance from a hammer. The construction. In order to avoid the use of shims, the backing structure was bedded down, placed on top of each sliding joint. A specially heavy ballast consisting of concrete for counterbalancing the aerial. This will ensure that the aerial can be made to tilt easily. However, not too easily, tilt from one side of balance to the other, and thereby introduce backlash. Steel weights will be fitted later to the elevation racks to complete the final process of balancing. The loaded concrete is then taken by skip up to the ballast compartment in the elevation rack and poured in. A vibrating machine will be used by the workman going inside to ensure that the concrete fills up all the internal nooks and crannies. Another operation is being carried out at the same time as the ballasting. The steel cantilever which is being raised is mounted on the strong ring to form part of the main backing structure which will support the outer ring of aluminium reflecting petals. The diameter of the reflecting dish which will be supported is over 82 feet, and the edge of it is about 81 feet above ground level. In a moment, as we view the aerial from the ground, we will see these ribs projecting out radially from the strong ring. When using the big reflector, a radio aerial and associated equipment will be placed at the focus. This operation involved tilting the aerial down, the first time it had been driven in this direction. This auxiliary aerial is called a feed and is supported by feed legs. There are 4 tubular legs, each 20 inches in diameter and 43 feet long on the Chilbolton aerial, and these are shown being raised into position 2 at a time. The backing structure of the aerial was designed to enable the base of each leg to be placed as close as possible to the edge of the reflector in order to minimize obscuration of the feed. It can be seen that there are 2 petals missing from the outer ring. These were left out to facilitate fitting of the top 2 legs. A most important feature of this aerial is the accuracy of the profile of the reflecting surface. It must be accurate to about 1/10 of an inch so that it can be used at radio wavelengths as short as 3 centimeters. 48 stretch-formed aluminium reflecting petals are used, 32 in the outer ring and 16 in the inner. Each petal is made from an aluminium honeycomb sandwich clad on each side with a skin of aluminium sheet 48 thousandths of an inch thick. A special lifting cradle is used for fitting the petals to prevent distortion. Each petal is mounted on adjusting bolts so that its position can be set accurately. The instrument being slung into the reflector is used to measure how much each petal must be moved to give the accurate parabolic shape which is required. It is called a parabscan. It is a special kind of optical rangefinder. It weighs about 1 ton and is hoisted into position using the aerial as a crane. When the aerial is tilted right up, the parabscan is lowered into its position in the middle of the aerial. We shall see more of the parabscan later and how it is used to find the position of a large number of datum points or targets which are stuck onto the petals. The National Physical Laboratory, in collaboration with AEI and RSRS, conducted a comprehensive series of tests to determine its accuracy. So far, we have been looking only at the construction of the aerial. At the same time, a laboratory building was being erected, and the aerial is controlled from here. This building can also be reached from the basement of the aerial tower by going along a tunnel through which interconnecting cables are run. It is made from standard concrete sewer pipes. In the control room stands the console from which the aerial is driven. The operator can see from the instruments and digital displays all that he needs to know about the position of the aerial. He also has a clear view of the aerial itself, which can be very useful for an instrument concerned largely with research work. The aerial can also be driven automatically from a control tape. All drives are electric, and the well-lubricated azimuth gear is being driven from the output of the gearbox attached to one of the 4 servo-controlled electric motors used in azimuth. Earlier, we saw the cable twister cone being hoisted up. Now we are inside the tower, seeing the twister in operation, preventing the cables from tangling. The 2 elevation drive pinions are connected by a torque tube which couples the 2 sides of the aerial rigidly together through the elevation racks. We now return to the use of the parabscan, which is the instrument used to measure the reflector profile accurately. The men entering the reflector bowl are preparing the parabscan for survey. The instrument can be used with the reflector set at any angle of elevation, but in this case, the zenith position is being used. The man climbing the feed leg will prepare an illuminated datum plate used in aligning the instrument. Whilst the instrument can be used during wet weather, it is protected when not in use by a tarpaulin cover. As the camera descends, beyond the man removing the green tarpaulin, another man can be seen adjusting the stays which support the parascan when the aerial is tilted. The illuminated datum plate is placed above the spider, which is used to carry the feed and associated equipment. The man on the reflector is looking at several of the 600 yellow datum points or targets which are distributed over the reflector surface and whose position is to be measured by the parascan. The operator who takes the measurements is seated under cover in the hub of the backing structure. The instrument is used to measure distances by sighting the targets through a pair of telescopes and associated pentaprisms. The readings thus obtained are fed into a computer which produces a readout showing the amounts by which each petal mounting bolt must be adjusted to produce the paraboloid of best fit. The petals are here seen being adjusted to this best fit paraboloid by using a torque spanner on the special adjustable mountings. These mountings allow for differential thermal expansion but remain stiff, normal to the reflecting surface. The aerial reflector has now been set and the aerial is ready for radio equipment to be installed. The design and construction of this instrument have taken over 2 years of close collaboration between electrical, mechanical and civil engineers, both in the government departments concerned and in the works and design offices of the contractors and subcontractors. A program of research on radio wave propagation, atmospheric physics and radio astronomy has already been planned, which will extend over several years, and there will be further applications continuing well into the future.
Fundamental research into the propagation of radio waves. That is the main job of the new steerable aerial facility at Chilbolton. Opened in April 1967 by the Secretary of State for Education and Science, Chilbolton is one of the many advanced research tools at the disposal of the Radio and Space Research Station of the Science Research Council. Soon after the official opening, radio apparatus was installed at the aerial focus so that the research program could start. But within a few months, there was trouble. A squealing noise could be heard coming from the azimuth bearing, the one which enables the aerial to rotate horizontally. A 13-foot, 15-ton ball bearing containing nearly 200 balls, the azimuth bearing is mounted on top of the tower and allows some 450 tons of aerial steelwork to rotate smoothly and to be pointed to an accuracy of about 20 seconds of arc. Tracing the source of the noise meant a considerable program of work, and careful measurements were made on the bearing over several weeks. It was found that the loaded race of the bearing was sinking at the rate of 10,000ths of an inch per month, a considerable amount. So, for safety's sake, the bearing was offloaded onto hydraulic jacks, and rotation in azimuth was stopped, although a number of radio experiments could still be carried out with the aerial operating in its altitude motion. This was the problem then. How to take out a one-piece ring, 13 feet across, weighing 15 tons, and replace it with another. Because a very stiff, movable structure was needed for research purposes, the bearing was in a very inaccessible position, more or less in the middle of the cabins slung underneath the aerial, and rotating with it. Failure was considered so unlikely that no special provision for removal had been built in. The low risk didn't justify the cost. When, against all the odds, failure did occur, the best method of removing the bearing had to be decided on. This was to raise the 450 tons of steelwork off the bearing by special jacks resting on top of the concrete tower, and then to withdraw the bearing sideways through the slot specially cut in the superstructure. But before deciding on the final details of the method, much checking was needed to ensure that none of the reinforcing and supporting ironwork fouled the aerial structure. The massive new ironwork had to be introduced into the aerial in components small enough to be threaded through the slot or hold up the middle of the concrete tower. To see how it was done, let's look at a cutaway drawing of the superstructure. The blue part is the main rotating platform, which has to be pushed up above the concrete tower, together with the bearing, coloured purple, which was then withdrawn to the right. The original position of the bearing is shown by the dashed line. Hydraulic jacks, 2 of them are shown in green, raised the platform. Massive steelwork, yellow in the drawing, had to be installed between the platform and the jacks to transfer the forces to the strongest part of the platform. The jacks themselves bore down onto the angled shoulder of the tower. Steelwork in the form of 2 four-legged spiders took up the forces within the tower. The upper spider was in tension, while the lower, in compression, was pre-compressed to a computed value by a flat hydraulic jack before lifting started. With the superstructure jacked up, the bearing was withdrawn in a cradle on rollers running in extensions of the main beam supporting the platform through the slot in the superstructure. Then it was lowered to the ground by crane. Installing the new bearing of the same dimensions as the old was simply a matter of reversing the whole process. To make room for the reinforcing spiders, the cable twister within the tower had to be cut into sections and removed. After the bearing had been replaced, the sections were bolted together again and put back. Strain gauges on the upper spider tell the controlling engineer the tension in each leg, and by resolution of forces, the upward thrust exerted by each hydraulic jack on the aerial structure. Each of the 4 pedestals, with its 120-ton jack, had to be mounted on the sloping shoulder at the top of the concrete tower. So 4 carefully positioned holes, accurately marked out, had to be cut in the surrounding skirt by oxyacetylene burners. Specially made wooden mock-ups of each pedestal established feasibility and helped planning. Our preparatory work included grinding the surface of the rotating platform to mount the bearer beam installation. Meanwhile, the 20-foot slot, through which the bearing was eventually to be withdrawn, had been cut in the aluminium cladding of the radio cabins after considerable internal reinforcing had been undertaken. Through this slot, each of the 4 jack pedestals, weighing over 1 ton apiece, had to be threaded on a porter beam past the internal machinery to its seating on the tower. Maneuvering the pedestals along the beams towards the slot was made easier by the use of a mobile hydraulic platform, a cherry picker, which was used for inspection at all stages of the work, however awkward the angle. The pedestals were eased through the slot and into their final positions. There wasn't much space, and care had to be taken to avoid damage to the azimuth drive pinions, which mesh with the gear wheel cut on the surface of the bearing. Locating pads were cemented onto the concrete surface of the tower where the pedestals were to rest before being attached to the tension rods passing through the tower to the upper spider. The lower spider was always in compression, forced outwards against the concrete with a known force provided by the hydraulic pad. The readings on the strain gauges on the upper spider, which was in tension, were continuously monitored at a central point back in the machine cabin, close to the manually operated hydraulic pumps which provided the oil pressure for the jacks. Continual monitoring in this way enabled the lifting forces of the 4 jacks to be maintained in the correct proportion to ensure minimum distortion of the rotating platform. The aerial was lifted about 1/8 of an inch at a time, and the pressure and strain gauge readings correlated. The distance by which each jack raised the superstructure was measured on a graduated scale, and as the aerial rose, a nut was gradually tightened back on a massive screw thread which would take the weight if the pressure failed. Clearances were constantly monitored, and as the aerial rose, lifting the bearing with it, gauges were inserted to check that it parted uniformly from the capping ring. When the hydraulic plunger reached the full extent of its travel, the weight of the aerial was taken on the screw thread and nut. The plunger was returned and an extension piece inserted between it and the screw thread to enable further lifting to take place. Ultimately, the whole of the 450-ton structure was raised about 8 inches above the capping ring on top of the tower, enough to clear the dowel pins and also to enable a steel cradle to be built around the bearing so that it could be withdrawn horizontally on rollers. Normally, the bottom of the aluminium structure would be level with the pathway. After lifting, the 8-inch clearance allowed the bearing in its cradle to be pulled along the projecting beams by draw vices. Then it was lifted above the supporting beams and lowered to the ground by crane. The headroom for the cranes was barely adequate, and great care was necessary to ensure that the aerial superstructure was not damaged. Although the whole operation was designed to be capable of taking place in winds of gale force, it was still considered prudent to take the precaution of installing a dummy bearing, just in case. During the 2 weeks before the new bearing was due to arrive, a dummy was installed and the aerial lowered back onto it for safety. The old bearing was taken away to the factory for opening up and inspection, and the seating ring removed for fitting to the new bearing. A fortnight later, the new bearing arrived from the factory by special transporter, angled to reduce the overhang of the load when on the public highway. After being unwrapped, the bearing was examined for possible damage. Of a stiffer construction than the old, the new bearing contains 2 sets of rollers at right angles. The original bearing was of the wire race type containing balls, not rollers. A calculated amount of flexibility had therefore to be built in, and was provided by rectangular compression pads on top of the bearing. Dowel pins underneath the bearing had to be located accurately with the holes in the capping ring on the tower. The cradle on which the bearing was to be rolled into position was attached and lifting started. The procedure was of course the same as before, but in reverse. The dummy bearing had been removed the previous day so that everything was ready. The cranes were put in the positions which had been required to enable the old bearing to be withdrawn without damaging the aerial superstructure. After the machine surfaces of the bearing were oiled, it was winched over the rollers. Cramped conditions meant slow, careful movements, but gradually the bearing was drawn in. During lowering, frequent checks were made on the clearances to ensure that the bearing was bedded down correctly. Any jamming might have distorted the bearing, preventing it from providing the very accurate motion necessary for the operation of the aerial. Its progression was carefully checked to ensure that the dowel pins would finish up above their respective holes. Finally, the bearing was completely home. Each dowel pin was exactly above its hole, ready to be lowered in. The lifting equipment installed within the aerial was completely dismantled and stored on the site at Chilbolton, just in case of another failure. With intensive work, the whole rig could be installed and a new bearing inserted in about a month. Failure is most unlikely, but with the great stiffness of the Chilbolton mount, unique in the world in this respect, uneven loading of the bearing could happen. It is the price one has to pay when research demands such high pointing accuracy.